Hello everyone, this is Mr. Appel, and today you are going to learn some things that you need to know to be able to do your very first proof, which we will do in class tomorrow. Before you start this video, you should have already completed the Introduction to Proofs matching exercises, Part 1 and Part 2 on Schoology. You absolutely need to know all of the different properties that came up in those exercises. So any ones that you didn't know after submitting them and looking at the correct answers, you should look up and make sure you know those properties, because without them you cannot do a proof. Okay. So to start, I'm going to show you what a proof would look like in a context that you're probably familiar with, solving an equation. So you should pause now to write that equation down, and then I'm going to show you how solving for x would look like, what it would look like in the form of a two-column proof, which is what most of the proofs that we do in this class are going to look like. So this is called a two-column proof because we have a statement and then a reason. So you make a claim and then you back it up with a reason. So to start, we're going to always start every proof, and I mean every proof, with stating what was given to us. So in this case, what was given to us is the equation. So step one is easy. We restate what was given to us, and the reason we know that that statement is true is because it was given to us. So you actually get to just say given. So if all else fails, you can always start a proof off with that. Okay. Now, if you're solving an equation, the next step would be to distribute. And you notice there's two cases where you can distribute, one on the left and one on the right. So it's actually okay to do both of those in the same time, on the same step, since the reason applies to both steps. So you can save a step. So my second step in solving this problem was to distribute. So I show what I did on the left, and then I back it up with a reason on the right, and that's simply the distributive property. So I'm going to go ahead and write the distributive property as my reason for that step. Okay. Now the next step is going to be to combine like terms, or to simplify. So that's not really one of the properties that you saw earlier, but if I'm just combining like terms, if I'm just simplifying the left side of the equation, it's okay to just say simplify as my reason. So I'm just going to rewrite what I don't have there. And my reason there would be simply simplify. I'm just simplifying the expression. So my next step would be to subtract the 7x from both sides of the equation. So I'm going to do that. So now I have 12x minus 30 equals 14. How did I get that? I did that by subtracting equal things from both sides of the equation. I subtracted 7x from both sides of the equation. That's the subtraction property of equality, so that's going to be the reason that I give. And it's perfectly fine to abbreviate there. The next step is to add the 30 to both sides. So I'm adding equal things to both sides of an equation. That's the addition property of equality. So doing that gives me 12x equals 44. So I'm going to back that up with a reason, which again is the addition property of equality. My last step is going to be divide both sides by 12. So that, of course, is going to be the division property of equality. And that is the gist of what a proof looks like. Every step that you make, every claim that you make, you have to be able to back it up with a reason, with how you know that that's true. Now we're going to talk about conditional statements. A conditional statement is basically an if-then statement. So it's a claim that's saying if something is true, then something else is true. And then we might be interested in whether or not that is in fact a true statement. So here's an example. If today is Wednesday, then tomorrow is Thursday. So there are certain parts of that sentence, and you need to know the vocabulary, so you want to write this stuff down. The hypothesis is effectively the if part. Whoops. Wrong tool. The hypothesis is the if part, which is today is Wednesday. It's not the word if, it's just today is Wednesday, so that's my claim. The conclusion is the result, which in this case would be tomorrow is Thursday, because I'm saying if today is Wednesday, then tomorrow is Thursday. So the hypothesis is today is Wednesday. The conclusion is tomorrow is Thursday. Another term you need to know is the converse. So the converse of a conditional is just when we basically flip it around. So the hypothesis becomes the conclusion, and the conclusion becomes the hypothesis. So in this case, the new sentence, the converse of our original sentence would just be, if tomorrow is Thursday, then today is Wednesday. Now let's talk about whether or not these statements are actually true. So the original statement, if today is Wednesday, then tomorrow is Thursday, I think you'd agree that that is always a true statement. Okay? Now what about the converse? In this case, the converse says, if tomorrow is Thursday, then today is Wednesday, and that also happens to be true. Now just because a statement is true doesn't mean its converse is true, and I'm going to show you an example of that. So here's another example. The hypothesis, in this case, again, is the if part, and the hypothesis would be I am, whoa, that's a typo, that should just say I am 13, sorry about that. Let's just fix that right here. I am A13 is a little weird. So the hypothesis should say I am 13, and the conclusion is the then part, I am a teenager. The converse of the statement, again, we switch the hypothesis and the conclusion, so that would be, if I'm a teenager, then I'm 13. Now let's look at the truth values. The original statement, if I am 13, then I'm a teenager, I think you'd agree that that's true. Because if you're 13, you are a teenager. But now let's look at the converse. If I'm a teenager, then I'm 13. Well, that statement is false, because you could be 13, but you could be 14 or 15. So here, you remember we talked about the word counterexample. This is a great example of using a counterexample. So if you want to prove that this is false, just come up with a counterexample. So I could say this is false, and I know it's false because you could be 14. That would be a counterexample, and that proves that the statement is false. Now to finish up, I'm going to show you a few different examples of how you work through a proof, how you can deduce things from information that's given to you. So we're just going to look at a couple of almost mini proofs just to get you the feel of how a proof is going to be formed, how you're going to put a proof together. So here's an example, and this is something we've talked about a lot. It says that L is the midpoint of line segment AM. Yeah, I know there should be a little bar over that AM. So it says line segment AM. Okay, so now my question is, what can you deduce from the given information? Well, L is a midpoint of AM. What's a midpoint? What's the definition of a midpoint? Well, the definition of a midpoint is, if L is a midpoint, then AL is equal or congruent to LM. So that's what you can deduce from it. How do you know? Because that's the definition of a midpoint. So what that would look like in a two-column proof form is this. So if I'd ask you to prove that segment AL was congruent to segment LM, you'd have a very easy two-step proof. Now obviously the proofs we'll do will be a little more involved from this, but again I'm just trying to get you started here. So let's look at another one. So this one looks like the last figure, and in fact it's kind of saying the opposite. It's the converse of the definition of a midpoint. So the definition of a midpoint said that if L is a midpoint, then AL equals LM. Here it's saying the converse. The given is that AL equals LM. So what can you deduce from that? You can deduce that L is a midpoint. So if that's what I was trying to prove, again, we'd have a two-step proof. It would just be the opposite of the last one. So let's see what that would look like. So notice that our reason is still the definition of a midpoint, even though it's the opposite. And what we're going to talk about a little bit more as we get more definitions is that definitions in almost all cases work in both directions. In other words, the definition and its converse are going to both be true. We'll talk more about that later. So take a look at this example. You think you should pause here and see if you can do this one on your own, and then I'll show you what it should look like. So hopefully what you wrote looks something like this. We stated the given and then deduced that angle ABD must be congruent to angle DBC because that is the definition of an angle bisector. If you wrote that the measure of angle ABD is equal to the measure of angle DBC, that's also true and perfectly okay to deduce from the fact that it's an angle bisector. They both mean the same thing, so either would be fine.